All right, so let's start. Uh, we had looked at CMOS inverter, and we had looked at its static characteristics, including the inverter threshold voltage, noise margins. Let's next look at the next important characteristics, which is the propagation delay. And for the propagation delay, as you recall, what we've been saying is that you apply an input of some shape with certain input may have certain rise time and a certain fall time, and in response the inverter would of course when this goes from input goes from low to high, the inverter would go from high to low, and we define propagation delay, high to low propagation delay, tau PHL, as the separation time interval between the 50% point of the output and the 50% point when the input crosses that particular point here. All right, so that's the difference. The two is tau PHL, and similarly, when the output is rising here, so tau PLH, that's also from 50% point to the 50% point here. So these are the definitions for propagation delay, high to low and low to high. And besides that, we have the rise time that you see here, the time taken to go from 10 to 90%, and we have the fall time, again 10 to 90% definitions here. So the most important ones are tau PHL and tau PLH. These are the ones that we normally use to indicate how fast is the inverter. Tower and tau F are also important, but relatively less so. All right, so what we want to do is understand propagation delay and find out the factors which determine the propagation delay of an inverter. As I said, inverter, although we are discussing inverter in great detail, the other gates are all very similar. Whatever we say about an inverter is true in general about other gates also. So let's look at the propagation delay. So we have a CMOS inverter, and as I said, normally when we look at propagation delay, we add a load to it, and the load for us is another inverter of the same kind. So we are interested in the propagation delay of this inverter, and the load is of this particular one that you see here. And the propagation delay, we said, can be understood using these two expressions here. Tau PHL and tau PLH, both can be understood these expressions. All that it says is that we are interested in switching this particular node from ground to VDD or VDD to ground. And at this particular node, we have a capacitance, and the capacitance needs to be charged and discharged. And so if I have a capacitance, net capacitance at this particular node, these capacitors are varying with bias, but if I define it as some average capacitance here, the capacitor needs to be charged or discharged by 0.5 VDD, because that's the interval that we are defining for delay, from 0 to 0.5 VDD or VDD to 0.5 VDD here. So the total charge that has to be supplied or extracted is 0.5 VDD multiplied by CT. That's the charge that has to be supplied, and this is the current. When you're pulling it up, the PMOS supplies the current. When you're pulling it down, the NMOS supplies the discharge current here. So accordingly is the pull down current from M1 or pull up current from M2. So in effect, the propagation delay can be understood through this two very simple expressions. It's basically a ratio of capacitance and current multiplied by the voltage here. So what we need to do is find out what is the capacitance at this particular node. And we need to find out what is this discharge current or the charging current. We need to find these two things, and then we have an estimate for propagation delay. All right, so let's look at the low to high propagation delay. The net, as I said, if you look at it, the transistors are all naturally, as the voltages are changing, the transistors are also making a transition. They're going from one state to the next state here. So the moment I take VDD to 0, abruptly bring it to 0 here, this transistor immediately goes into cutoff. This was initially in when it was VDD here, this transistor was cut off, right? But the moment you bring it to 0, the transistor turns on, and when it turns on, the output voltage is still 0 here, and gate voltage is also 0 here. So it starts off with saturation region. It starts off with saturation region, and then as the voltage charges here, eventually goes into linear region, right? So that's how this particular transistor is, during this transition here from low to high propagation delay here, this remains cut off. This goes immediately into saturation and goes to linear. This one, well, starts off, note that initially is 0. M3 initially is 0, so it's in cutoff. Then it will turn on and may go into saturation and linear, so it turns into here. Similarly, this may start off in the linear region and eventually note that this is charging, so this will eventually go to VDD here. And as it goes to VDD here, this will turn off. So it starts from linear, goes to cutoff eventually. All right, so all these are making transitions. All these transistors are, except for this one, which becomes, let's say, cutoff. The transistors are changing states. The voltage at this particular node obviously is changing. And if the voltage at this node is changing, the voltage at this node is also changing. Because if this is switching, then this will cause the second inverter to switch also. Right? So all these things are changing. And the capacitors are, to calculate is a little bit involved, but at least we can see conceptually what the capacitors are. So in the black font, I've shown here the capacitors associated with my inverter, the inverter that I'm interested in, the switching of that particular inverter. So you can see here there are capacitors. If I look at this particular node, the capacitors come from this transistor M1 and will come from M2. And M1, if I look at it, again, this is the drain part here. So there is a drain to gate here, gate to drain capacitance here, CGD N1. N refers to NMOS, and M1 here, CGD N1. And then this is between drain and body. Body is connected to ground, so CDB N1. So those are the two capacitances associated with M1, which contribute to this particular node. And similarly, this is a complementary design, so whatever is true for M1 will also be true for M2. So there is gate to drain of P2. So there is drain here, and there is gate of this one. So gate to drain of P2, and drain to body of P2. So drain here, and body is connected to VDD, and VDD is at a fixed potential, and we had discussed this here, so you can put this also drain to body of P2. So those are the capacitors associated with the first, with the inverter itself. And so CGD1 and CGD P, they depend basically on the widths of these transistors here, the length and the widths of these transistors M1 and M2. And if we have that information, one can calculate these things easily. The drain to body obviously depends on the drain area and the perimeter. So you have to know the perimeter and the area of this transistor, the drain of this transistor, and the perimeter and the drain of this particular transistor. So we need to look at the layout and figure out what the areas are. And these, all right, so these are for this transistor. Now at this particular node, we also have capacitance contribution from M4 and M3. So from M3, if you look at M3, there is a gate to source capacitance here, the CGSN3, and there's a gate to drain capacitance here, CGDN3 here. And there is a gate to body also, body is connected to ground, so there's a gate to body capacitance also. So 3 capacitors in contribution coming from M3, right, to this particular node. And similarly, whatever is true of M3 is also true of M4, so 3 other capacitors. So, so these are intrinsic to my inverter. I mean, these are part of my inverter. These you can consider as part of the load, because they're coming from the second stage. So these are like the load. So total capacitance that you see here, CT, some part is this, the one in the black is intrinsic. We can call it intrinsic capacitance. This part we can call it the load capacitance here, because it's coming from this load here. So each one of them we have to estimate and find out what the values are. And as I said, these are functions of bias. They depend on the state here. So all that we can do in analytical calculation, quick calculation, is get a rough estimate here. So these are very important capacitance, drain to body and of N1 and drain to body of P2. So as I said, you need to do the layout or have some estimate for the area of the drain and the perimeter of the drain. So this is our inverter with 4 lambda by 2 lambda here. So NMOS has been drawn to 4 lambda by 2 lambda, and PMOS has been drawn to 8 lambda by 2 lambda here. And the area of the drain then it's simply geometry. So we need to calculate, figure out how much is the area of the drain here. So it starts from here, goes up. All this region is n plus here. So whatever is the n plus region here, the whole part is the drain. So that comes out to be 40 lambda square. And perimeter of the drain, so you have to start from here, go up here, go towards the perimeter here. You can verify, comes out to be 22 lambda. The area of the drain of PMOS, PMOS, note that its size is twice as large as this, 8 lambda by 2 lambda, but its area of the drain is not twice as large. It's not simply 80. It's 50 here. If we go again and look at the area, so it's 50. And the perimeter of the drain, if my calculations are correct, it comes out to be the same here, 22. Anyway, so the point is that you need to do the layout, and from the layout, look at the perimeter of the drain, area of the drain, have these values here in order to estimate the drain capacitance here. So I've given you a rough, we have expressions for all of these terms here. And as I said, they depend on the state. So for example, gate to drain N1. So we know the size of this particular one. It is 4 lambda. Lambda for us is 0.3. So 4 into 0.3 is 1.2 micron. So gate to drain N1, I've just taken the overlap capacitance. Gate to drain has an overlap and a channel capacitance. So that's about 0.3 femtofarad. Drain to body of N1. Drain to body N1, we have area drain, perimeter drain, but it also depends on, it's a PN junction capacitance, it depends on the bias here. So this is a zero bias capacitance, about 6 femtofarad. This is gate to drain of P. P is twice as large as N. The width is twice as large, so its capacitance contribution is 0.6 here. Drain to body of PMOS, we saw that the area here and the area here were almost the same, and the perimeters are also the same. So note that these are approximate values. These are 6 femtofarad here. So you can see that the inverter itself contributes 6 plus 6, 12 at about 13 femtofarad. That comes from my inverter itself. And the load part here, these two together add up roughly the gate capacitance. When I look into my transistor here, the gate capacitance is about 2 femtofarad, 2.5 or so, 2 femtofarad here. The gate to source of this one is about 5 femtofarad here. So roughly the load here contributes to about 7 femtofarad. So total capacitance is 13 plus 7, about 20 femtofarad at this particular node. Note that 13 deliberately I've written in blue, indicating that it belongs to the inverter, and 7 is the load that's coming from the load here. All right. So for example, if at this particular point I had not connected one inverter, suppose the fan out had been 2 inverters. One more inverter, suppose I had connected, this would have become 7 into 2. It would have become 14 femtofarad, while this would have remained the same as 13 femtofarad. All right. So it depends on the load here. So 13 plus 7, so we have roughly 20 femtofarad of capacitance at this particular node, average value at this particular point here. So that's how we go about estimating, for a quick calculation of what the delay is, go about calculating what the capacitance of this particular node is. All right, the next thing is, note that, so fine, we have an estimate of capacitance. We know VDD. VDD for us is 3.3. And then we need to calculate for delay. We need to calculate, let's say if I'm looking at high to low delay, where this particular node is going from VDD to ground, I need to calculate the pull down current here. So pull down current, note that this is off, so discharge current is nothing but the current here. So if I look at this node here, the node here is going from VDD to ground. So it starts from VDD. This is VDD here. The transistor starts off from saturation. Now, as this voltage falls, eventually the voltage will go to VDD minus VTHN. VDD minus VTHN is nothing but the saturation voltage of this transistor. So the moment the voltage falls below the saturation voltage, the transistor enters into linear region and stays in linear region throughout. Right throughout, all this region is the linear region here, but we are interested only in this till this point here, because tau p HL is from this point to this point, 0.5 VDD. So part of the region it is in saturation region, part of the time, and part of the time is in linear. So it's a bit complicated what IPD is. It's a function of time. But what we are going to do is calculate it at the beginning and calculate it at the end of the this thing and take an average. So at the beginning of it, note that at the beginning of it, it would be KPN, WN by LN, the size of this one, multiplied by VDD. Input is VDD minus VTHN squared by 2. So that's the current here. And the current will stay the same as you start from here and go up to VDD minus VTHL. It's a constant current. Constant current, so capacitor discharges almost linearly. Constant current here. The moment you come here, the current starts decreasing. It goes into linear. So at the end of it, it's in linear region, so I calculate it using here. KPN WN by Ln, the expression for linear region VDD minus VTHN. The effective drain to source voltage at this point is VDD by 2. This is VDD by 2 at this particular point, so VDD by 2 minus VDD squared by 8. So that's the expression that we have for the current at this point. Now we have all these values, KPN, WN, Ln, everything we have, so we can calculate. So I am taking this as 4 lambda by 2 lambda. So this current comes out to be 0.53 and this current comes out to be 0.487. So fortunately for us, we find that the current doesn't vary too much. And we can take an average of this. The average comes out to be about 0.5 milliamperes. So in an inverter like this, we have about half a milliampere current available to discharge a capacitance, which was 20 femtofarad. So we can easily now calculate, put 20 femtofarad here, put 3.3 volt here, put half a milliampere here, you get a delay of 65 picosecond. So that's how we estimate tau PHL to be 65 picosecond for this particular inverter here. And if I do a more accurate calculation, I'll show you some simulation results later on, where we don't assume this average capacitance and average current here. The answer comes out to be about 75 picosecond. So 65 is what we get. The accurate answer is about 75 picosecond. So we are not too off in terms of the numbers here. But more important is we can see where is the delay coming from. What is the source of the delay? What is roughly the current here? Who's causing the discharge? Where the capacitance are coming from? So all of this we can see from this particular expression. Now, if I break this up, 65 picosecond, note the capacitance has had two parts. 20 femtofarad, 13 was from the inverter itself, and the load had 7 femtofarad. So I can break this delay into two parts. 42 picosecond is the, you can say, is the intrinsic delay of the inverter. And 23 picosecond comes about because of the load. If I didn't have the load, this thing, then the tau PHL would have been only 42. But because of the load, I get an additional delay because the additional capacitance has to be charged discharged. So that's 23 picosecond. All right, so that's the high to low delay, and the circuit is fairly symmetrical, as you can see here. Whatever happens with NMOS, similar things happen with PMOS when I go from low to high. So very similar. Tau P LH 0.5 CT VDD in now case is pull up, and the pull up, which means it starts from ground and goes to VDD here. Initially the PMOS is in saturation region, then it goes into linear, and we have chosen the PMOS size as 8 lambda by 2 lambda. If you recall, we did that because PMOS mobility or KP for PMOS is smaller, so we increased the size here to balance the current of these two to get a symmetrical VTC. And so even though the KP is smaller here, KP is half, the size has been doubled. So this part is the same as the NMOS. And so we get exactly the same. 0.53 here, 0.487 here, pull-up current is 0.5, delay again comes out to be 65 picosecond. So in the simplified analysis, we have kept the size exactly double, and so the delay here also comes out to be 65. All right, so we get an estimate of, note that if we had not kept at 8 lambda by 2 lambda, if we had not doubled the size of this one, if we had kept it 4 lambda by 2 lambda, what would have happened is that the current would have been half of what you get here. The current would have been about 0.25 milliamperes. Now, 0.25 milliamperes here doesn't mean that the delay would have doubled, but as you half the size here, the capacitors and all that would also reduce something, right? But you would get a discrepancy between the tau PLH and tau PHL. You won't have the same delays. In fact, if I made the size of PMOS the same as the size here, the pull-down delay would be smaller compared to the pull-up delay. So that's another reason to balance the delays also. We make the size here twice the size of this particular one, roughly twice the size of this one. All right, so we have tau PLH and tau PHL. This is how we estimate here. So you can see a sort of comparison between the two here. How we go about estimating the low to high, high to low, and the the low to high delay here. Now, in all these calculations of capacitance, I included drain to body and drain to body here and all that. To be more accurate, note that when I have two inverters connected in one after another, so this is how the two inverters look like. So I took into account the capacitance of the drain here, the capacitance of this particular drain here, but in between, note that this metal that connects the one inverter to the next inverter, this particular one also has a capacitance, so that was not included in the analysis here. So if you want to do more accurate analysis, if you go back to the CT here, we need to add an additional capacitance, which is the interconnect capacitance. This metal is used to interconnect one inverter to the next, so interconnect capacitance will also come. Because we have put the two inverters right next to each other, adjacent to each other, the interconnect is not very large. So there's not going to be too much error. But if this inverter had been far from this particular inverter, then the wire capacitance, we've discussed this earlier, would have been more significant here. So if you want to do more accurate calculation, calculate the area here of this particular one, the perimeter of this particular one, and from there the manufacturer tells you what is the capacitance of metal 1 per unit area and what is the capacitance of metal 1 per unit length, the perimeter, the fringe part here. And you can, once you have the area and the perimeter, you can calculate this capacitance and add to this node here, CT. So it would be 20 femtofarad plus, I don't know what the value is, 1 or 2 or whatever femtofarad additional comes in, we'll add to that particular part. All right, so the delay that you see here, I've been saying that delay comes about because of this expression that you see here. And CT is made up of two parts. CT is made up of an intrinsic part, intrinsic to the inverter, and a part which is because of the load here. So we can break the delay, as I've been saying, into two parts here, intrinsic delay and an extrinsic delay. And intrinsic delay, so this was 13 femtofarad and this was 7 femtofarad here. Now, intrinsic delay is not exactly, but roughly constant. Roughly constant, constant with respect to the size of M1 and M2. These values that you see here, I did the calculation assuming this was 4 lambda by 2 lambda and this was 8 lambda by 2 lambda. Now suppose I take each one of these transistors and I double their size. So this becomes 8 lambda by 2 lambda and this becomes 16 lambda by 2 lambda. So I'm doubling the size of M1 and M2. So roughly what would happen is if you double the size, the pull-down current would double. The pull-down current would double, and the argument is if I double the size here and double the size here, the capacitances will also increase. Not exactly double, but would also increase maybe proportionately. And so as I increase this, this also increases, and this first term remains approximately the same. Intrinsic delay. Note that the word is approximate. CT and this thing, intrinsic and IPD don't scale in a similar manner. But the idea is that it's roughly a constant with the sizes here. If you double it, you can make the M1 size 4 times larger and M2 4 times larger here. This may not change that much. But the second one for a fixed load capacitance here, if I double the sizes of this M1 and M2, what would happen is the pull down current would double and this part of the delay will become half. Because the load capacitor, let's say, is fixed. I attach a fixed capacitor here. If I make the sizes 4 times, then the delay will become even 1/4. So this delay that you see here, extrinsic delay, I can change it by changing the sizes here. So I can write here tau p for the high to low. There's an intrinsic delay which we found was 42 picosecond. And this delay which was the remaining 23 picosecond or so, but I can write this as 0.5 VDD and IPD here that you see here. So I can take 0.5 VDD, IPD, multiply them together and write it as a factor A, and CL writ in terms of femtofarad. So I get a value of A equal to 3.25 picosecond per femtofarad here. So what is this telling you? Note that everything has been normalized to picosecond. So what this is saying is the delay of this particular inverter is 42 picosecond, which is intrinsic, will always be there. And the remaining will depend on how much load capacitor you add. And how does the delay increase? Well, it increases linearly with CL. If I add more CL here, the delay will increase linearly. So if I plot tau p HL versus CL, I'll get a straight line, and the slope of it would be what? A. And A is what? 3.25. So it says 3.25 picosecond per femtofarad. So for every 1 femtofarad of capacitance that you add, the delay will increase by 3.25 picosecond. Or other ways you can say, for every 1 PF of a capacitor, the delay will increase by 3.25 nanoseconds. All right, so this is like the slope here. So this factor A is important. So when I'm characterizing a gate or an inverter, whichever gate, NAND gate or whatever. So what I would like when I characterize and I want information about the gate, what I would like to know is how much is the intrinsic delay and how will the delay increase with the load capacitance. Because once you give me this expression, then I can sort of predict, depending on what I connect to my inverter, 2 inverters, 3 inverters, whatever I connect, I can get predict what the overall delay for this particular one is. All right, so I'll show you, I'll show you some results from the 180 nanometer, what these values are in a minute here. So this is important, this equation. So when you finally when you design your inverter and you want to tell somebody how, about the delay of an inverter, you have to give an expression like this. What is the intrinsic delay and what is this factor A? How does the delay increase with the load capacitor here? So you have to specify both these things here. So the inverter that we've been talking about, 4 lambda by 2 lambda, 8 lambda by 2 lambda, I can call this inverter a 1x inverter. What do I mean by 1x inverter? Well, this is the minimum size that I can use for my NMOS. 4 lambda by 2 lambda is the minimum size that I can use. And to balance the currents, I have to make this 8 lambda by 2 lambda. So this is in some sense the minimum size inverter that I can make. So 1x means size is 1, the smallest size of inverter that I can make. Note that the delay of the inverter would go like this. We have said intrinsic part and extrinsic part. Now I can do the following. I can delays here. So what I can do is next I can make an inverter which is double the size here. And if I double the size here, I will have to double the size here also. Otherwise, the inverter would not, VTC and all that would not be symmetrical. So I do this here. This would be called a 2x inverter. An inverter which of strength 2 as compared to this particular inverter. Now, size, of course, size may not actually increase twice. We have seen the size does not scale immediately with this particular one. It may not be exactly twice the size of this particular one. You'll see some numbers in a minute here. But what would happen is, note that as you make this double the size here, if I look at the delay of this particular inverter, what we are saying is approximate value. The intrinsic delay would remain the same. Right? Because I've doubled this, so current would double, capacitances would also, let's say, double, intrinsic delay would remain the same. So if I were to write an expression like this for this one, it would be same 42. Again, please, I'm again reminding, this will not be exactly 42. It will change, but roughly, let's say 42. It would also be A times CL. But note what has happened to A. A is 1.625. Why is it 1.625? Because note that you have double the size, so the pull down current has become double. So that's why we are saying this inverter has a strength. What do I mean by strength? When I'm saying this inverter is twice as strong as this particular inverter. Strong in what sense? Well, its ability to drive the capacitors. This is a strong inverter. Its ability to drive the capacitance here. So note that if you add 1 femtofarad of capacitor here, its delay will only increase by 1.625 picosecond, while this one would increase by 3.25 picosecond. This is stronger. You can load this particular inverter and its delay would not increase as much as compared to this one. So this is twice as strong as this one. And I can make another inverter which is 4 times strong as this one. So this will be called a 4x inverter. Its delay, if I load it with 1 femtofarad, it would be half of this. It will not increase as much. So this is 4 times. So people will have various kinds of inverters. 1x inverter, 2x inverter, 4x inverter, 8x, 16x. Okay, so let's see this example here. Now, the issue is, why don't I make my inverter stronger and stronger, 4x and 8x? One is, of course, the area is increasing. As I go from 1x to 2x to 4x, the area of my inverter is increasing. So area is always important for us. But in terms of delay, you are saying, well, delay is improving. The intrinsic delay is remaining the same, and its ability to drive load is actually reducing. So delay-wise, it appears as if it's improving. But there's one factor here. As you, let's say, go from 1x to 2x, yes, delay is improving according to this expression. But who's going to drive this inverter? Somebody has to drive this inverter also, right? Who is going to drive it? Let's say there is another inverter which is driving this inverter here. What happens when I look from here? What would be the capacitance of this particular one? When I double the size here, what will be the input capacitance here when you look from here? That's going to increase. The input capacitance of this particular inverter is going to increase. So if I have an inverter like this, and suppose this inverter is driving here, now this particular inverter is driving here. So when I double the size, the load of this particular inverter increases. Right? So yes, you improve this inverter. You improve this inverter, its ability to drive, but this inverter also has to be driven by somebody, right? So its input increases. Its input increases here. So now this poor inverter has to drive more load. So it will suffer. Its delay will go down. So it's not so easy to simply increase the size here and expect that overall inverter delays would increase. You also have to pay attention to who is driving it. So note that what I'm introducing is one more thing about a delay. So yes, this expression like this is important. Intrinsic delay and the driving ability, this factor A, let's say, is important. But along with that, another thing which is important is what is the input capacitance. So when you're characterizing an inverter, you're characterizing a gate, you have to give this value, you have to give a value of A, and you also have to specify what is the input capacitance, because that's important. It's important for the preceding gate. That information is important here. All right, so with this information, let's look at this 0.18 micron CMOS technology. The supply voltage for this is 1.8 VDD. And the manufacturer of this one particular manufacturer has a data sheet. And in the data sheet, he says that I have available, you can use it, these kinds of inverters. 1x, 2x, 3x, 4x, 8x, 12x, 16x, 20x. All these inverters are available. Use it. Whichever one is suitable for you, you can use. Now, the areas, you can see how the areas are scaling. So this is my 1x inverter, let's say. You can see how the area is increasing. When you go from 1x to 2x, the area is not really doubling, 1.3 to 2. Or when you go from 2 to 3 and 2 to 4 and all that, you can see how the area, you can plot it out and you can check it out. You can multiply the height and the width of the cell, and you can plot it against the strength, and you can see how the area is increasing. Check this out. All right. This is a special cell which is a low power, specially designed low power cell here. So that's something different. So ignore this for a moment. Just look at X1, X2, X3, X4. So what the manufacturer is basically doing, basic inverter is there, and the size of NMOS and PMOS are being basically doubled. Double, triple, 4 times, 8 times, and things like that. All right, so that's how the inverter is being designed. Now, what are the parameters of the inverter? They are here. Take some time to look at the parameters. I've highlighted the 1x inverter. See if all the parameters that you see here make sense to you. Ignore the first one for a moment. Ignore the first one. Look at these ones here. So look at the first one. What is the manufacturer listing? The capacitance at this particular input capacitance here. Listing 0.0036 in picofarad. That's the input capacitance. That's an important information. All right. The other information that the manufacturer is listing is the intrinsic delay. The intrinsic delay is 23 picosecond when you go from low to high. Output high goes from low to high is 23 picosecond. And the high to low is 14 picosecond. So it's asymmetrical here. The design is not very symmetrical, is asymmetrical, 23 and 14 picosecond. These are the intrinsic delays. And instead of, I've used that parameter A, the manufacturer has this parameter which is same as A, which says how does the delay increase in nanosecond per picofarad. All right. So these are these factors here. 4.5 and 2.4. For us, if you go back and see, our factor was 3.25, let's say. And so here it is 4.5 and 2.4. So for high to low and low to high. So this is the information that you see here in red. This is the information that you have to supply. Now, along with that, the manufacturer is also listing that if you take this node A and you toggle it, you apply a clock, how much power is dissipated because of this capacitance here. So dynamic power is CT, VDD squared times F. So if you take dynamic power, divide by F, you get here basically in watts per megahertz here. So if you apply 1 megahertz here, you'll get some power here. So you get 0.0114 microwatt per megahertz here. So it's listing the power dissipated because of the capacitance here. So note that if I take this inverter and connect it to somewhere, so this particular inverter to some node, so this particular inverter is going to add some capacitance to that particular node. How much capacitance does it add? It is here 0.0036. And if that node is switching at 1 megahertz, as a result of this inverter, so much power will be dissipated. So that's why this is being listed here. So whenever you add an inverter to a particular node, this inverter is going to cause so much power to be dissipated. If you switch it, power in terms of megahertz here. So many microwatts per megahertz here. So this is the sort of data sheet that we have for an inverter. Now, if you go from X1 to X2, as I said, intrinsic delay, note that intrinsic delay is not remaining constant, right? 0.023, 0.020, then it goes up 0.022, 0.018, well, 0.018, 122, 119, 117. Roughly, maybe you can say it's constant, but there is some change, intrinsic delay. 8 to? Yeah, 8 to 12, I don't know what happened. 0.018, so up till this point, 0.122, why this is going, I don't know. I'm not sure what happened or why this is there. But this one, if you look at the scaling factor, that's scaling more with the size here. 4.5 here and becomes roughly half here. And 2.25 here, when you make it 4 times, becomes 1.1. And I don't know if you check here, does it become 16? What happens here? All right, so this is how we characterize our inverter. There is a input capacitance, there is intrinsic delay, and there is how the delay increases with the load capacitance. All right, so the capacitance that we have been talking, the delay that we have been talking about is for an inverter like this, and we switch the inverter abruptly. But note that this is not a typical inverter. What I just analyzed is not a typical inverter. If I look at a chain of gates or chain of inverters, this is more typical. Why is it more typical? Well, it has a load. Every inverter or every gate will have a load. So it does have a load and is being driven by another inverter. Here we drove it from VDD to 0 or 0 to VDD. That's not going to happen. Most of the gates and all that will be driven by a previous gate. So this is a more realistic inverter here. And it's more realistic to see what happens to the delay of this particular inverter rather than this one. This is a rare situation. From the pin, let's say you drive it with a very sharp, you'll find. Now, we calculated, if I simulate this particular inverter, I get a delay of 75 picosecond. We calculated 65, but simulation gives us 75. Reason why I'm using simulation is because I'm giving you results from simulation for this one. Now, so this is 75 picosecond. And the delay of this particular one, 134 picosecond. Huge difference. Delay of this one is 134 picosecond. Look at that. High to low of 75 picosecond. Now note, it's not what is it due to. When I go from 75 to 134, the load capacitor of this one is the same as the load capacitor of this one. It's not because of the changes in the load capacitance. This inverter also has a load of this one. This inverter also has a load here. So it's not because of the load. And what causes changes in delay? There are only two factors. Remember, delay is 0.5 capacitance times VDD divided by current. If capacitors are the same, then the delay must be coming about because of changes in current. The current must have changed for some reason. But then you may say, well, these transistors are the same. Why are the currents changing? Well, let's look at that. Let's see why has the delay increase so much, 134 picosecond versus 75. So note what has happened here. Now I've put here a gradually rising input. Now what is discharging the current here? Note it's obvious what is discharging the current is this one. But IDSN minus this current here, ISDP. IDSN minus ISDP equal to minus CT dV out by dt. So what is discharging is this current minus this current. Now earlier what I was saying was, well, I've gone from 0 to VDD abruptly. 0 to VDD abruptly. So what happened was, this transistor got its full input VDD immediately, and this transistor switched off immediately. This is not happening now. This transistor will not get a VDD immediately. It starts from 0 and goes up to, it takes some time to reach VDD. So, its current is gradually increasing. It doesn't reach its full current immediately. And further, this transistor does not switch off. So it's subtracting from here. Both these reasons are causing a decrease in this particular current. IDSN is not what it was earlier because the gate voltage is not VDD. And ISDP is not 0 because this transistor has not switched off. And as a result, the discharge current is smaller. So PMOS does not switch off immediately. NMOS does not reach its full current drive capability immediately. And both these reasons are causing propagation delay to increase. Now, it becomes complicated. How is it increasing? How much, it depends on how much time does it take. And, the calculation then becomes messy. And that's why I'm not attempting it. There is no analytical expression as such. We can tell exactly how much. But what people do use is an approximate expression like this. That tau PHL, let's say, is tau PHL 0. This is for abrupt transition. So tau PHL is tau PHL square plus the rise time or the fall time divided by 2 square. This is the rise time or the fall time of the input. So your actual delay increases with, it's an empirical expression, it's not been derived. It's just that, you look at how tau PHL varies with the rise time or the fall time of the input, you plot it out, fit an expression, and you find this expression works reasonably well, so you use this. Okay, so this is something very important to remember here. Propagation delay depends on the rise time and the fall time of this one, and can depend so much. Go back and look at this one. 75 picosecond versus 134 picosecond. It depends a lot. So the numbers that I was quoting you were some sort of best case here. So if you have to quote a propagation delay, then how do you quote? What do you do? What would be a more realistic propagation delay? So what people do is, I've not shown here, what people normally do when you have a new technology and you want to quote a propagation delay. What they do is that they take these inverters, and you can take an odd number, 5, 7, 9, and make a ring oscillator. Take this here, input, and connect it back here. Right? So you can take 3, and then it becomes an oscillator. You can take 5, it becomes an oscillator. Take 7 and all that. So normally, for example, let's see if I don't have a data sheet here. So for example, for this 0.5 micron technology, what the manufacturer would do is, would take this inverters and make let's say a 31 stage ring oscillator. 31 such inverters connected, ring oscillator, and will quote what is the oscillation frequency of this ring oscillator. At what frequency is it oscillating? 31 stage ring oscillator, at what frequency is it oscillating? So that's a better measure of, because each node is switching. This gets its input from here. This is also rising, falling, and all this. So that's a more accurate. I'll come to that a little later on. We'll talk about this later on. Some more things about process. The delay, so what I said was delay is a function of the rise time and the fall time of the inputs. There's another complication. I've been giving you, KPN or all of these as if all the transistors have the same KPN, same VTH. When you're making millions of transistors, there's a variation. All transistors do not have the same KPN. KPN, if we break it up, is made up of mobility and oxide capacitance. All transistors do not have the same mobility. There are variations. All transistors do not have the same threshold voltage. There are variations. Now, the variations And so what we can do is we can classify what the manufacturers many times do for simplicity. They call a transistor as a fast transistor or a slow transistor or a typical transistor. Typical transistor would be, let's say KPN is supposed to be, we are using 100 microamperes per volt square. That's KPN. And we are using VTHN as 1 volt. That's a typical value. Typical value means if I measure, let's say, VTHN for, say, 1000 transistors and I plot them out, the mean value would be 1 volt. The mean value would be 1 volt, but there would be some transistors with a threshold voltage of maybe 1.1. And there may be some transistors with the threshold voltage of 0.9. So it's going to lie within a range. It's sort of a bell-shaped curve, right? So VTHN is varying. Similarly, KPN is also varying. So now imagine a case where, let's say, KPN is, let's say 3 sigma. We take 3 sigma. So KPN is 3 sigma above mean. And VTHN is 3 sigma below mean. What would its impact be on the current? Suppose we take only plus 3 sigma and minus 3 sigma. We just look at that. So let's look at a device whose KPN is 3 sigma above the typical value and VTHN is 3 sigma below. Would you say, can I call that transistor as a fast transistor? Can you see why I may call it a fast transistor? KPN is 3 sigma above and VTHN is 3 sigma below, which means the current is high. You know, that's the sort of the maximum current that you can get. And maximum current, capacitances are not changing that much. Maximum current here. So the delay would be minimum here. So we call such a transistor as fast transistor. With the minimum VTHN and with the maximum KPN, that would be called as a fast transistor here. And the opposite of it is a slow transistor. Slow would be maximum VTHN and minimum KPN. We call that transistor a slow transistor. And then we have a nominal or a typical transistor here. So we have, you know, if you think of variations, you can think of now 3 kinds of transistors I can potentially get in my system. A fast transistor, a slow transistor, and a typical transistor. Now when I'm making an inverter, well, if I'm lucky, I'll get nominal, typical. But what else can I get? I could get NMOS slow and PMOS also slow. So I can get slow, fast, slow, fast. I can get all these things here. Right? So let's say this is the typical VTC for a moment. What would a slow NMOS and a fast PMOS look like? What will happen to the VTC? Slow NMOS and a fast PMOS. What would happen to the VTC? Now, what does slow mean? Slow NMOS mean the current in NMOS is lower, and fast PMOS means the current in PMOS is higher, which means PMOS is a bit stronger and NMOS is a weaker. Stronger means my output. What does PMOS do? PMOS tries to maintain the output to VDD. And what does NMOS do? Pulls it down. So can you all see that this is what would happen? Fast P, slow N. My VTC will shift towards the right. And what about the opposite one? Slow P and fast N. Right? So now you have all these VTCs which are changing. This may be a typical VTC here. This may be another VTC with a fast and a slow, and with a slow and a fast. So when somebody is designing circuits, these are called process corners. My process can go slow, fast, slow, fast, slow. It's like the corners of the process. And we have to evaluate our inverter at all the process corners. Okay, so here I'm looking at 2 extreme cases, fast, slow here and slow, fast here. And we have to make sure that we get noise margins and all that which are adequate in both these cases. At this point, this extreme case and this extreme case here. So we need to evaluate. Similarly, we need to look at delay under these process variations. So, so the next thing I'll show you is, and besides that, the temperature is also going to vary. The supply voltage will also vary, and process corners we've already seen. So now with all of these, what is the worst case delay that you can get? What is the best case delay that you can get? You have to characterize that also. Okay, so all right, so let's stop here.